Through these particular short recent videos in this lecture series, we've just shown the icing on the cake, or only the tip and small part of this whole world of mathematics, which has been studied for over 125 years since the realization or presentation of Hilbert's problem. We looked at recent particular results in the last 25 years concerning the derivation of fluid mechanics equations from the fundamental laws of mechanics and put them on a more contemporary framework. We've shown that the full derivation of the Navier-Stokes equations from Isaac Newton's laws is still, even now, widely open in terms of like a really fundamental, rigorous mathematical derivation. And this is due to our lack of understanding the derivation of the Boltzmann equations mostly, which is still a topic of study. One of the particular reasons this derivation fails to hold for large times, is because we're unable to understand the fundamental properties of the Boltzmann equation, that is, the entropy dissipation at levels of like the particular particles, at least mathematically. There's much more done in chemistry and physics. There's many other open problems that are available for attack from young and excited people, or maybe old and wise, and that's the short-time derivation of the Boltzmann equation, which, as you might recall or be stated, is an assumption that the particles are identical spheres of mass 1 with very small diameter, and it could be even relaxed a little bit more to masses of comparable size, and that the particles could involve in a periodic box of size 1, denoted by math script Td of dimension d, and even other situations where you could use the whole or infinite space. Going from the Boltzmann equations to the Navier-Stokes equations does hold some difficulties also. In particular, nothing is really known in the derivation of the Boltzmann equation in a domain with boundaries, except that the problem can be reduced to the whole space or to a periodic box with symmetry, which is something like an infinite space too. So you can see there's many difficulties in the problem still. In this case, the particles still interact elastically in each particular binary collision, and there's no other type of interaction or even forcing, so it's very limited relative to physics we're interested in. And it can be more general interaction potentials is very interesting and relevant. This is being considered under very, very strict assumptions and not very successfully. So far in the class, we mostly focus on derivation of incompressible Navier-Stokes equations and a little bit on the compressible or full Navier-Stokes equations. All that really remains to be done with the particular first limit of the Boltzmann equation when alpha goes to infinity with no time real scaling is the compressible Euler equations, let alone compressible Navier-Stokes.